Hi, today I'm going to talk about a very significant result in the theory of linear and time-invariant systems, namely the calculation of the output signal when the input is a complex exponential signal. Now, remember that the complex exponential signal is given in the following form: e to j omega 0 t, where j is the imaginary unit and omega 0 is the angular frequency of the complex exponential signal. So omega 0 is the angular frequency. And also remember that x of t is expressed by means of Euler's formula, cosine omega 0 t plus j sine omega 0 t. So the complex exponential signal is complex valued. The real part is a cosine signal and the imaginary part is a sine signal. Now, what happens if we apply this signal as the input signal of a linear time-invariant system? So we have a linear time-invariant system, and the input of our system is denoted by x of t, the output is denoted by y of t. And also we remember that the linear time-invariant system is characterized by its impulse response. H of t is the impulse response of the system. What do we mean by the impulse response? When we apply an impulse, a unit impulse, as the input signal, the output obtained or created by that input signal is called the impulse response. And in a previous video, we have seen that if you know the impulse response of the linear time-invariant system, you can calculate the output corresponding to any arbitrary input signal x of t by means of the convolution operation. That means x of t and h of t are convolved to obtain y of t, and the convolution integral is given by means of this expression x of tau h of t minus tau d tau. Well, by a simple change of variables, you can also write the convolution integral as h of tau x of t minus tau integrated with respect to tau. That means the order of multiplication in the integral is not critical. In other words, in more mathematical terms, we claim that convolution is a commutative operation. X convolved with h is equal to h convolved with x. Now let our input be, let our input signal be the complex exponential signal e to j omega 0 t. Okay. Therefore, corresponding to this input signal, the output will be from minus infinity to plus infinity, h of tau, x of t minus tau integrated with respect to tau, which is equal to from minus infinity to plus infinity, h of tau, e to j omega 0 t minus tau integrated with respect to tau. Now you see that e to j omega 0 t is a term which can be taken outside the integral, and the remaining integral expression is h of tau e to minus j omega 0 tau integrated with respect to tau. Now let us assume that this integral is a convergent integral. That means this integral exists. Now later we are going to discuss under which conditions this integral exists, but at the moment let us not concentrate on that aspect, but let us assume that this integral exists, and let us denote it by h of omega 0, because here, although we have taken omega 0 as a constant, the only parameter in this expression is omega 0, because the integration is with respect to tau. So we call this expression, the result of the integral, capital H of omega 0. Therefore, y of t is capital H of omega 0 e to j omega 0 t. Now, what type of a constant is h of omega 0? H of omega 0 is a complex constant. So this is a complex constant, which means that we can express it in polar form as in terms of its modulus and in terms of its phase. Therefore, y of t is modulus of h of omega 0 e to j omega 0 t plus phase of the phase term h of omega 0, the argument of h of omega 0, or angle of h of omega 0, and we get this expression. Now here we observe that we have obtained a significant result. When the input is the complex exponential signal, the output is also a complex exponential signal, the same complex exponential signal, but multiplied by a complex constant. That means only its magnitude is changed by means of the system action, and the system action introduces a phase term. Okay, so how can we interpret this result? That will be our next question. Okay, now we can try to interpret our result. Now we have obtained the following result. In fact, we have a linear time invariant system, and the input is e to j omega 0 t, the complex exponential signal, and the corresponding output is h of omega 0 e to j omega 0 t. Now, what is this h of omega 0? This is a complex constant which is obtained from the impulse response of the system. This is the impulse response. In terms of the following operation, h of omega 0 is equal to, from minus infinity to plus infinity, h of tau e to minus j omega 0 tau integrated with respect to tau. Of course, provided that this integral exists, but we are going to look at that condition later. Therefore, for fixed omega 0, h of omega 0 is a complex constant. Now, this result is analogous to the following result in matrix theory. Okay, so we are going to try to establish an analogy. Let A be an n by n matrix. The vector x is an eigenvector of A, and lambda is the corresponding eigenvalue if the following relation is satisfied: ax is equal to lambda x. In other words, the eigenvector problem is interpreted as follows. Remember, when you operate a matrix on a vector, you obtain another vector. But if the vector is an eigenvector of the matrix, when you operate the matrix on the eigenvector, the operation is equivalent to multiplication of the vector by a scalar. So, in other words, the matrix operation on the eigenvector is equivalent to scaling. Okay? That means the vector is essentially unchanged but only scaled by multiplying it by a scalar. Now, you see that in our case, in the LTI system, we have a similar interpretation. In fact, the same interpretation. The system action is analogous to the action of the matrix in the theory of matrices. So the system action of this linear time invariant system on the complex exponential signal is just a scaling of the complex exponential signal by a complex constant. Therefore, in LTI systems, x of t in the form e to j omega 0 t is an eigenfunction. of the system. So here our input is e to j omega 0 t, and the corresponding output is y of t, which is equal to h of omega 0 e to j omega 0 t. And you see that this is a scaling action. Scaling action. Essentially, the input is not changed. It is the same exponential, complex exponential function, but only scaled by means of a multiplication by a constant, a complex constant, which means that the complex constant contributes in the following way. The amplitude, the original amplitude, which is equal to 1, is now modified as the new amplitude, which is modulus of h of omega 0, and the initially zero phase in the input signal is now modified. We have the phase introduced by the system action. Okay. So we have obtained a very significant result, which tells us the following. For linear time-invariant systems, complex exponential signals are eigenfunctions. The system action on the eigenfunction, as the name implies, is just a scaling operation, multiplication by a constant. And we are going to make use of this result in several applications in the coming videos. Now we have only a single detail left. As you remember, I have told that we obtain the scalar or the constant h of omega 0 by means of this integral, provided that the integral exists. So what can we say about the integral? Under which condition can we claim that the integral exists? Now, we must for the existence of h of omega 0, which is equal to this expression, this integral must be finite. In other words, the magnitude of the integral h of tau e to j, we have a minus omega 0, and also our integration is with respect to tau. Okay, for the existence of this integral, the magnitude must be bounded. This must be bounded. Okay. So we ask the following question: is this integral convergent, or does it satisfy this condition? Okay, now let us look at the magnitude of this integral, minus j omega 0 tau d tau. Okay, this is less than or equal to the integral of the magnitude of the integrand. But we can further write it as the magnitude of h of tau, the magnitude of e to minus j omega 0 tau, and integrated with respect to tau. Now, it is clear that the magnitude of this term is equal to 1. The modulus is equal to 1. Why? Because real part of this is cosine omega 0 tau. Imaginary part is minus sine omega 0 tau. Therefore, when we evaluate the modulus, we have squares of these two terms, the cosine and sine, which adds up to 1, and therefore the magnitude is 1. Therefore, this integral is convergent if, okay, then this term becomes the integral of magnitude of h of tau. H of tau is the impulse response. So we obtain the following result. If this integral is convergent, that means it's a finite, it has a finite value, it acts as the upper bound of this integral. We are trying to find whether it exists or not. We are trying to obtain the answer for the existence question. So we have the following result. H of omega 0 exists. That means it is finite. It can be calculated by means of this integral, or the integral is convergent, provided that the integral of magnitude of the impulse response is finite or convergent. This integral is convergent. It exists. Okay? So if this condition, as you see, this is a condition completely related to the impulse response of the system. If this condition is satisfied, as you see this expression, if this is finite, then therefore this integral here, this expression is bounded by a certain finite value as an upper bound, and therefore the integral exists. Later we are going to see that this condition that should be satisfied by means of the impulse response is related to a system property, namely stability. In other words, if the system is stable, the impulse response is absolutely integrable. We call the existence of this expression, or this expression being a finite quantity, but finite value, we say that h of t, the impulse response, is absolutely integrable. So absolute integrability of the impulse response implies the existence of h of omega 0. In other words, when we have a linear time-invariant system and we have a complex exponential signal as the input signal, the output is a complex exponential signal multiplied by a constant, but that constant is obtained in terms of an integral expression, and that integral exists provided that the impulse response is absolutely integrable. Thanks for listening.